Uh-huh. Okay, again, good evening to everyone. So the lecture for tonight is sparse matrix solution techniques. Okay, essentially, we're going to talk about how are we going to, we're going to talk about some techniques when dealing with sparse matrices. Okay, so you may be wondering, why are we talking about sparse matrices? Okay, so take note, guys, that our class, that when we were building the Jacobian or the bus admittance matrix for an electric power system, recall that for the bus admittance matrix, the diagonal elements are non-zero, meaning there is always a value dun sa diagonal natin. Okay. Now for the off diagonals, we only get a value in an off diagonal if there's a branch connecting the buses corresponding to the column and the row. Okay, so for example, if we're looking at row 1, column 10, the value or the value there will be 0 unless there is a branch connecting bus 1 to bus 10. Okay, if there's a branch connecting bus 1 to bus 10, then we will simply put the negative of the impedance at that particular cell. Okay, and then otherwise, the value of the cell will be 0. Okay. Now, in a typical power system, on the average, a bus is connected to 3 other buses. It's rare that you will see a bus connected to 10 other buses or 20 other buses. Okay, so pag nakakita tayo ng power system, usually it's a bus will only have, say, 2 or 3 branches emanating from it. Okay. So if there are 3 lines connected to a bus, then it's connected to 3 other buses. Okay. So if you have a big power system and you write the Y bus for that, the bus admittance matrix, then most probably the matrix that you will get is sparse. It's already given that it's a large matrix. Okay. So if you have a power system with 500 nodes, then the bus admittance matrix would be a matrix which is of size 500 by 500. Okay. However, if a bus is connected only to 3 other buses, then on that row, wherein you have 500 elements, you only have 4 elements that are non-zero, meaning all of the entire row will be mostly 0 except for 4 values. Okay, one of which is the diagonal, and the other 3 are, well, corresponding to the 3 branches. Okay. That are connected to that buses. Okay. Now also recall that when we write the Jacobian in our load flow, we are dependent, or we are using the values in the bus admittance matrix. Okay. So if the bus admittance matrix is sparse, then expect that the Jacobian is also sparse. Okay. So imagine you have a large sparse matrix, and then you're going to invert it, meaning you're going to get the LU factors. Okay, then and then what's the point of getting of performing some multiplications or some mathematical operations if you already know beforehand that the result will be 0? Okay, and that's primarily because most of the elements are 0. Okay, so if you already know that you're going to add 0 to 0, or if you're going to multiply 0 to another number, okay, why bother doing such arithmetic arithmetic process? Okay, if you already know that the answer is 0, diba? So that's what we're trying to take advantage of. If we recognize that a multiplication or an addition or a division would result in an answer equal to 0, then let's find a way to identify those steps and avoid them altogether. Okay, I think that idea will become closer, not closer, clearer as we move on. Okay. Now another issue on large matrices, especially sparse matrices, is that if you already know that most of the elements are 0, then why bother storing that value? Okay, so imagine if you have a matrix that is 500 by 500. So the size of that matrix would be what? 25,000. Okay, and if you're going to store that matrix, 25,000 ba? No. It's 250,000. Okay, that's a large matrix. Okay, 250,000. So if you know that most of the elements are non-zero, then why bother storing those the zero elements? So in this example here, no, if you have a 1,000 bus system, okay, you have a 1,000 by 1,000 matrix, and if four elements of a particular row is non-zero, it means that only 0.4% of the elements are non-zero. And if you're going to store the entire matrix in memory, sayang naman, you're wasting 99.6% of the space if you already know that 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 it is zero. Why allocate space for a value that is already zero? So you just have to store maybe that 0.4% and just have to find a way to remember where that 0.4% belongs to. Okay. So on the first part of our slides, we're going to talk about, actually the slides talk about storage methods, but I'm going to skip them now. Okay, I'm going to skip them. I think there's still value on learning the storage methods. I trust that you will be able to understand this when you go to this. I'm going to skip the lecture primarily because storage is no longer a problem. Okay, so we know that as time goes on, okay, as time goes by, the cost of storage decreases with time. Unlike before, say in the 1970s or in the 1960s, computer storage is very expensive. So if you already know that most of the elements are non-zero, or are zero rather, then it's a big deal that if you waste space to store a value that's equal to zero. However, right now, diba, the cell phones that we use, the thumb drives that we're having, we already have thumb drives with 32 gig or even higher memory space. So memory is no longer an issue. Okay. Now the issue that we're going to focus on is the derivation of the LU factors. Okay, so say you already have a big matrix. You know that most of the elements are zero, and then you're going to compute for the LU factors. So obviously, if you have a matrix that is mostly zero, then expect that the LU factors are also zero. Okay, and if you recall the Kraut's method, actually the Kraut's method is seen here. Okay, ito yung Kraut's method ng LU factorization. You will see here that there are multiplications, that there are divisions happening. Okay, now if you already know that the answer will be zero, then perhaps we could spend time by skipping all of those multiplications, skipping all those divisions where the results will be zero. Okay, take note that if you're going to perform LU factorization for our full Newton-Raphson method, recall that we have to build the Jacobian, we have to invert the Jacobian, and our preferred choice for the inversion is to get the LU factors. Okay, so it means that we have to invert that big matrix in each iteration. Okay, and we want that inversion to be as fast as possible. Okay, and we can accelerate the speed of the computation if we can skip some of the processes that we know that the answer is zero. Okay, so one way to reduce the amount of computations that we have to go through is to reorder the nodes. So when we say we reorder the nodes, okay, recall that say we have a power system. We assign a particular bus as bus 1, another bus is bus 2, another bus is bus 3, etc., etc. Okay, reordering means we will simply change the ordering. We will change the numbering of the buses. So yung original na bus 1, pwedeng hindi na siya yung bus 1, yung the original bus 2, it could be assigned as another bus number. Okay, and take note, guys, that when we were building the bus admittance matrix, we usually assign the first row and the first column to bus 1, di ba? Second row and second column to bus 2, third row and third column to bus 3. Okay? So if we're going to reorder the matrix or reorder the power system, it means that the first row and the first column will no longer be assigned to a bus 1, to the original bus 1. Okay? We will choose a new bus 1, we will choose a new bus 2, and we will choose a new bus 3. And by doing so, we will be able to reduce the number of arithmetic operations like multiplications and divisions. during the LU factorization and the backward and forward substitution process. Take note that when we're using a calculator, multiplying and dividing is very simple. You know, we just have to input the number, we just use the multiplication button, and then we just click the equal button, and we will get the result. But internally inside the computer, a lot of things are happening there. Okay, multiplication and division is not as straightforward as it seems. It involves, it's a complex process if it's being implemented by a computer. So imagine that a computer, it uses binary representation to the numbers. Okay, so imagine you have two binary numbers and then you have to multiply them or you have to divide them. Okay, it takes a lot of effort from the point of view of a computer. And just imagine if you're going to perform the LU factorization and the backward forward substitution, then it means that the inversion process would take a lot of time. Okay, now the ordering scheme, essentially our target here is to reduce the number of fields. I haven't described yet what I mean by a field. No, I will show that to you later, but I'll just mention here lang that the objective of the reordering or the ordering scheme is to reduce the number of fields in the Q matrix during the LU factorization process. Now, what's the Q matrix? Recall when we're doing the LU factors, parang we assign one matrix arbitrarily as the Q matrix, and then the lower diagonal of the Q matrix would be the L, and the elements at the below the diagonal is L, and then the elements above the diagonal is U. Okay, so please go back to your lectures. Meron tayo doon on a few slides where we talk about the Q matrix, okay, as a proxy for the L and U matrices. Okay, now let's say that you have a big matrix, say 1,000 by 1,000. Okay, and let's say that it is a full matrix. So when we say a full matrix, each element is non-zero. Okay, all values in your 1,000 by 1,000 matrix is non-zero. Okay, now if we are going to perform the LU factorization for that matrix with dimension n by n, then the numbers that you see here, alpha and beta, alpha is the number of multiplications and divisions for the LU factorization process. And for the LU factorization process, alpha is equal to n cubed minus n over 3. So just imagine if you have, say, para simple na lang, 1,000. If you have a 1,000 by 1,000 matrix, n is equal to 1,000, then the number of multiplications and divisions is equal to 1,000 cubed. Okay, so 1,000 squared is 1 million. 1,000 cubed is 1 billion. Okay, so that's 1 billion minus 1,000 over 3. Okay, so just imagine how many multiplications and divisions that you have to do just to get the LU factors. Okay, but we will not stop there, because after getting the LU factors, we will still solve for the unknown using the backward and forward substitution process. And the number of multiplications during the backward and forward substitution process is equal to n squared. So again, if n is equal to 1,000, then it means that we have to perform 1 million multiplications and divisions in the backward-forward substitution process. Okay, so that 1 million may pale in comparison with the 1 billion. However, it's still an additional 1 million. Okay, so again, dun sa LU factorization process pa lang, the number of multiplications and divisions that we have to do is in the order of billions. Okay, 1 billion. Actually, hindi na nga 1 billion kasi we still have to subtract 1,000 from it. But still, it's 1 billion multiplications and divisions. Okay, I'll just give you here an idea, what I'm talking about. So let's say that you have a matrix that looks like that. Ito na lang yung order ng matrix natin. Okay, let's say that this is your Jacobian, or that could be your Y-bus matrix. And let's say we want to decompose that, meaning we want to get the LU factors of that. Okay, so to get the LU factors of that, yung LU natin is we have to create the matrix Q, and then after getting the matrix Q, all the elements above the diagonal, that is your U matrix, and then the diagonal and all elements below that, that's the L matrix. Okay, so that's how we get the LU factors. Okay, and then the equations that you see here, well, these are the equations that we use to get the elements of the Q matrix using Kraut's method. So, for example, here to get the Q matrix, we start with the A matrix. So, for example, that's the A matrix. So, to get the first column, we simply copy the first column. So, A11 is this one. This is A21. So, A21, that's A21. This is A31, A41, and then A51. Okay? So, we simply copy the first column to the Q matrix. Now, how about the first row? Okay, I hope you still remember the Kraut's method, parang first column, and then we proceed to the first row, and then the second column, and then the second row, and then the third column, and then the third row, and then the fourth column, and then the fourth row. We fill up those elements one at a time. So column, and then row, and then this column, and then that row, and so on and so forth. Okay? So, so for the first column, we simply copy the elements, okay, of the A matrix. Now, how about the first row? So for the first row, the value that will go here is equal to A12, the original value, divided by Q11 or A11. The value that will go here is equal to A13, the original value, divided by the diagonal element. The number that will go here is equal to the original value there divided by the value here. And then the number that will go here is equal to A15 divided by the diagonal element. So essentially ito yung ginagawa natin to fill up the first row. Okay? And take note, as we fill up the first row, we already performed four division steps. Okay? Now, let us proceed with the second column. So for the second column, we're going to follow these equations. Okay. So meaning for Q22, the value that goes here, it is equal to A22, the original diagonal element, minus this value times that value. Okay. So ito yon. Okay, the number that will go here is equal to the original value there minus this one times that one. The number that will go here is equal to the original value there, which is A32, minus this one times that one. Okay, the value that will go here is equal to the original number minus this one times that one. And then the number that will go here is equal to the original value minus this one times that one. Essentially, I'm just performing these equations. And in those equations, we have performed four multiplications. Okay? So kung di nyo na maalala to, just go back to the Kraut's method of LU factorization. Okay? Now, how about this row naman? This row, well, to compute the value that will go there, it's equal to the original value there, which is the A23, minus Q21 times Q13 divided by that value, okay? The Q22. The number that will go here is equal to the original value there minus this thing here times that thing divided by Q22. And then lastly, the number that will go here is equal to the original value, which is A25, minus this thing here multiplied by that thing divided by the diagonal element. So take note, guys, that as we compute for the values, the three values here, we are performing an additional 3 multiplications and 3 divisions. Okay, and as you follow and as we fill up the entire the table, the rest of the values, you see that okay, for Q33, Q40, and Q53, the elements that will go here, for each element, kailangan natin we have to perform 2 multiplications. Okay. And then as we fill this up, we have to perform 2 multiplications and 2 divisions. So two multiplications per line and then a division. And then as we fill this up here, we have to perform 3 multiplications. And then as we fill up this guy here, that's 3 multiplications and 1 division. Okay, so just imagine how complex the equation or the expression becomes as the expression becomes larger. Okay, so that's our main concern here. Okay, so as we go down, as we go further at the bottom or to the right side of the matrix, then we have to perform more multiplications and divisions. And that is because we have a matrix that looks like that. Okay, now before I proceed to the next slide, I just want to explain to you what this means. This means that the numbers you have 1, 2, 3, 4, and 5. Those are the node numbers, also corresponding to the row numbers and the column numbers. And then if there's a branch between two nodes, it means that there's a value at the non-diagonal element. So here there's a branch between bus 1 and bus 2. So it means that there's an element at row 1, column 2, and row 2, column 1. Similarly, there's a branch between buses 1 and 3. And that branch corresponds to this non-diagonal element here and diagonal element there. Okay, and so on and so forth. Okay, so in a way, we're using this network to describe the connectivity, or we're using this network, this connectivity to describe how the matrix looks like. Okay, now proceeding to the next slide. Okay. At this point, I'm going to define a fill. Okay, so when I say a fill, it means that in the original matrix, you have a position that is originally non-zero. Originally zero, like this one here. Okay, the value here is 0. However, based on this equation here, okay, that element which is originally 0, take note, A23 here, although meron tayong term dyan A23, the value of A23 is 0. Okay? That A23, which is originally 0, will now become non-zero because the value that will go there is equal to negative Q23 times Q13 divided by Q22. The original position, the original cell with a 0 value has become non-zero. So we will now say that a fill occurred at that position. A fill will also occur at this position, at the second row, fourth column, because of this term. Okay? So Q21 is non-zero, Q14 is non-zero, Q22 is non-zero. So even though A24, the value here is equal to 0, then it means that on the U matrix, the value here is not equal to 0. It will get that value. Okay, so essentially all the 0 values here will become non-zero, okay, because of all these expressions here. So these voids are filled. They are now filled. Okay, so a fill occurs in the Q matrix when an element that was original 0 becomes non-zero during the factorization process. Okay, now this is another way to demonstrate. So again, when we get the LU factors of that matrix, first we go to the first column, and then first row. Okay, so first row, first column, and then second row, etc. So when we're building the second row, nagkaroon tayo ng fills dun sa A32, A42, and A52. I think, sorry. Hey, go away. Ayun yung umalis. Anyway, paano ko ba ituturo yun? The label here is row, the label there is column. I think baliktad. The label here should be column, the label there should be row. Okay. Anyway, my point here is that there were fields in A32, A42, and A52. We are now referring to these values here. Okay. So they were originally non-zero and they have become 0. Okay. Similarly, while we're doing the second row, this is column, that should be column, that should be row. While we're doing the second row, the fills happened at A23, A24, and A25. Here, here, and here. Okay? So essentially, this table is telling us where the fills happened. Okay? Now, so here we can count the number of multiplications and the number of divisions. Okay? And then after getting the LU factors, we will now solve for the unknown. Okay? And that is through the backward-forward substitution. So the backward-forward substitution is shown here. Okay, so this is the forward substitution, that's the backward substitution. Okay, I hope you still remember that. And for example, on the first step, you have a division, and then you have a multiplication and a division, and then you have 2 multiplications and a division, 3 multiplications and a division, and so on and so forth. Okay, and then as we move on in the matrix, then we will encounter more multiplications and more divisions. Okay, now count after going to the process. Now let us count the number of multiplications and divisions. Okay, so using this formula here, or that in that formula there, okay, the number of multiplications and divisions required during the LU factorization process is 40. And then for the backward and forward substitution, that's 25. Okay, in fact, the table here, pinapakita sa atin the number of multiplications that happened and then the number of divisions that happened. So for example, in the first step of the forward substitution, there are 0 multiplications and 1 division. Okay, and then on the second step of the forward substitution, there is 1 multiplication and 1 division, and so on and so forth. Okay, so after adding all of this is what we will get. 25 multiplications and divisions, requiring a total of 65. Requiring a total of 65 multiplications and divisions. Okay. Now, how do we visualize a fill? Okay, so imagine we have a network that looks like that. So how would we know using this network that a fill happened? Okay, so take note that we are getting the factors. And as we get the factors, we are moving from one row to the next. So we start at row 1, and then column row 1, row 2, or this diagonal element here, and then that diagonal element, and so on and so forth until we reach this diagonal element. Okay, so when we are factoring, in terms of the first element of the first diagonal element, in a way, it is equivalent to removing that node from the network. The factorization of node 1 may be simulated as its removal from the graph. Originally, we have a graph that looks like that. If we remove node 1, pag nawala na si node 1, then we are left with 4 nodes that are no longer connected. Take note that if we take away the node, we will also take away the branches with it. So we are left with 4 remaining nodes. So those nodes are no longer connected. So we have to introduce branches to reconnect them to each other. And the branches that we reintroduce to reconnect them, visually, those are the fields, okay, in the network. So recall, bus 1 is originally here. When we remove that, we are left with 4 buses that are floating. And to reconnect them to each other, then we have to insert all of these branches. And each branch corresponds to 2 fields. A field that happens at row I, column J, and at row J, column I. So for each branch that we reintroduce in the network, we are encountering 2 fields. Okay? Now, what if we reorder? Okay, so originally this is our, this is the network. If we write, say, the bus admittance matrix, I hope you agree with me that this is how the bus admittance matrix will look like, diba? Kasi there is a branch between bus 1 and 2, 1 and 3, 1 and 4, 1 and 5. So you have non-zero elements at the diagonals here, okay, at the off-diagonal elements here. However, there is no branch here, hence you don't see an element here. The value is equal to 0. Okay. Now, what if for the same network we renumber? Instead of calling this as bus 1, we call it bus 5. We call this as bus 1, bus 2, bus 3, bus 4, bus 5. Okay. Now, if that is the network with the new number, then the Y bus will look like this. Okay. Now let us solve for the LU factors. For the LU factors, again, we will build the matrix Q. We copy the first column. Copy the first column. Ito yon. Q11, this one is equal to A11, and then all of these are 0, and then Q51 is equal to A51. Now, how about the element here? The element here is equal to the original value divided by that one. The value that will go here is equal to the original value there divided by that one. But the original values here are all equal to 0. Since we know that they are 0, we no longer have to perform these 3 steps here. We can, sorry, not those. These 3 steps here. Okay, these steps here. We can skip those steps already because we already know that we are dividing 0 by a number. So we can skip those steps, and then it means that we will be performing fewer multiplications and divisions. In fact, to construct the first column of matrix Q, the first row of matrix Q, we just have to perform one division. Okay, just one division. Okay. Now, how about the second column? Okay, so the value that will go there, we just copy. The value that will go here is equal to the original value there minus this thing times that thing. It's a 0 minus 0 times 0. We don't have to do that anymore. The value that will go here is equal to 0 minus this times that, which is also 0. All of them are 0, so we don't have to perform the multiplications anymore. Similarly, going to the second row, the number that will go here is equal to the original number minus this thing here times that number divided by this. So it's 0 minus 0 times 0 divided by that thing. The answer is 0. So we can skip the multiplication, we can skip the division. In fact, when you follow the Kraut's method, for a matrix that looks like that, this is the only process that you have to go through for the LU factorization. We only need a total of 8 multiplications and divisions. So you can see here that we only need 4 divisions. 1, 2, 3, 4. And we only need 4 multiplications. Kailangan si multiplication dito. Okay? The value that will go there is equal to the original value minus this times that, minus this times this, times this, minus this times this, minus this times that, which is that one. So 4 multiplications only. And then 4 divisions giving us a total of 8. So from an original of 40, it is now down to 8. So it means that the LU factorization process is now 5 times faster. Okay? Kasi from 40 steps, we are now reduced to 8 steps na lang. It's now 5 times faster. Okay? Now, how about the backward-forward substitution? So for the backward-forward substitution, this is what we have to do. And we are left with, please count na lang, we are left with 13 from an original of 25. Okay? So now let us add the total of multiplications and divisions. So originally you have 40 plus 25, that's 65. Now we are down to 8 plus 13 or 21. So by simply reordering the buses, assigning a new set of numbers, our process is now 3 times faster. From 65 multiplications and divisions, it's now down to 21. Okay? So, ang question now is, how do we reorder? How do we renumber? Well, the main idea here is, from an original structure of an arrow that is pointing to the upper left, we want our matrix such that most of the elements will concentrate at the lower right-hand portion. Okay? Here, originally, we have a matrix wherein the elements are concentrated on the leftmost and at the topmost column. Leftmost column and the topmost row. If there's a way to reorganize, to renumber the buses such that most of the elements will be concentrated at the bottom and at the same time at the rightmost column, then we are essentially eliminating or avoiding fields. In fact, when we performed the LU factors here, we didn't have fields here. Okay, the original 0 values, the original 0 cells remained 0. Okay, so that's our objective. How do we renumber the buses such that the elements are concentrated at the bottom and at the right? Okay, I'll give you this example muna, no? Okay, let's say that you already have this is your original matrix A, and let's say that you want to get the LU factor of that, and we want to compute for the number of multiplications and divisions. Okay, so the question is, this is your matrix A, you want to get the LU factors. Now let us compute for the number of multiplications plus the number of divisions. Okay, so alpha, the number of multiplications and divisions during the LU factorization process, is given by that expression. Okay, so simply put, start from row 1, and then from row 1 go to row 2, row 3, and so on and so forth. Okay, so as you go from the first row to the next until you reach the bottom, you simply count the non-zero elements in column I below the diagonal element plus 1, multiplied by the non-zero elements in row I to the right of the diagonal element. Take note, guys, that our Jacobian is usually symmetric. Okay, so it means that the number of non-zero elements in column I would be equal to the non-zero elements to the right of the diagonal element. Okay, so this is our expression. Mami, I'll show you how to apply that expression. I think that's easier. No, we just go straight to the application. Okay, beta is, you just count the number of non-zero elements of matrix Q. Okay, just count the number of non-zero elements of matrix Q. Okay, but if this is A matrix, then this will be the Q matrix. Okay, parang mali yata, parang nagalaw ng PowerPoint yung labels ko. This is the original matrix A. This is the new matrix Q. And then take note that in the new matrix Q, there are fields that are indicated by delta. Okay, so for example, here, this is a triangle. Originally, that is 0. It is 0 here at matrix A, and then it becomes non-zero. Okay, I hope you can imagine kung bakit siya naging non-zero. Okay, again, recall that to get the value that will go here, it's equal to the original value minus this thing multiplied by that thing divided by that thing. Okay, since this thing and that thing is non-zero, then you have a non-zero product, and then you divide it by that value. So yung original na 0 doon will become non-zero. Okay, similar to this thing here. Okay, bakit siya, yan, paano nagkaroon ng field dyan? Okay, paano nagkaroon ng value dyan pagdating dito? The value that will go there is equal to the number here times that 1. You may argue that is 0 multiplied by that 1. Okay, 0 yon. However, the number that will go here is equal to the original value there, minus this times that, minus this times that, minus this times that, divided by the diagonal element. Okay, so essentially I'm just performing this expression in that matrix. Okay, so this element here, which is originally 0, it has become non-zero. A fill happened there. Okay, now how about this element here? How come walang fill dyan? It is 0 here. It's still 0 here. Well, the number that will go there is equal to the original value. That's 0. Minus this thing times 0. Minus this thing here times 0. Minus this thing times 0. Minus that thing times 0. All the elements here are 0. Hence, the product will be 0. There will be no fills here. Okay. Again, you still have to divide by the diagonal element, but nevertheless, the values at the at the numerator are all equal to 0. Okay? So let's say that this is already your Q matrix. We will now use the matrix to compute for the non-zero, or sorry, the number of multiplications and divisions given by that expression. So you start at, just look at the diagonals, you start at the first one, and then you count the number of non-zero elements below it. Okay? Plus 1, and then you multiply by the number of non-zero elements to the right of that diagonal. So for the first element, for the summation here, for I equal to 1, it's equal to 3 plus 1 times 3, or 4 times 3. Yun nga lang pagdating sa equation natin, it has become 3 times 4. I cannot edit it, but this should be 4 times 3 instead of 3 times 4. But I get, but the answer will still be the same, okay? And then for the second time in the summation, this one, count the number of non-zero elements below it. So the non-zero elements are 1, 2, 3, and 4. Multiply that by 1, 2, 3, 4, and then plus 1. Hence, you have a 4 times 5. Okay? And then moving on to the third diagonal element, you have 5 elements here multiplied by 5 elements here plus 1. And then for the fourth diagonal element, you have 4 elements here multiplied by the 4 elements here plus 1. Okay? So hence, we have this expression. You do that until you reach the bottom, and we will get 134 alpha, or multiplications and divisions just to get the LU factors. Okay? We're not yet finished, because once you get the LU factors, you still have to perform the backward-forward substitution. And the backward-forward substitution is simply equal to the non-zero elements of matrix Q. So you just count the number of non-zero elements here, so all the dots and the triangles, they so happen to be 68. So you add 68 with 134, then the total inversion process requires a total of 202 multiplications and divisions. Okay? Now, let's go back to the original question. How do we reorder? How do we renumber the buses? Sino ngayon yung bago nating tatawagin na bus 1? Sino ngayon yung bago nating tatawagin na bus 2? And so on and so forth. Okay? I'm going to introduce 3 ordering schemes. Okay? We're going to call them scheme 0, scheme 1, and scheme 2. Okay? Again, our objective in the reordering scheme is to simply minimize the number of fields in the factored matrix Q to minimize the number of multiplications and divisions. Also, we want to minimize beta, which is the number of multiplications and divisions in the backward-forward substitution step. And our objective in the ordering schemes is we want the matrix to look like a lower right pointing arrow matrix. So a matrix wherein most of the elements are concentrated at the lower half and at the right side. We want them to look that way, an arrow that points that way. I don't know, no, ganon pala. I don't know what you see, but the point here is that most of the elements should be concentrated at the right side and at the bottom. Okay, so I will now introduce scheme 0. Please look at the steps. First step is we are to determine the degree of all nodes and vertices we list. So when we say the degree, well, the number of edges connected to it. Okay. And then choose the node with the lowest degree. And we will call that bus 1. Okay. So the bus with the least number of branches connected to it is bus 1. And then the branch with the second least number of branches connected to it, we call it bus 2. Okay. So choose the node with the lowest degree and place it in the ordering scheme. We'll call it the first bus. In case of a tie, choose the node with the lowest natural ordering. In case of a tie, so parang arbitrarily we can choose. So kung sino yung original na mas lower numbered, pwedeng siya na lang uli. Okay? And then we return to step 2. Okay? I think the best way to describe that is through the example. So we will now have, I think I'll still use the original example. That's the original example that we have here. Okay. So take note, if we did not reorder, the number of alpha and beta is equal to, alpha plus beta is equal to 202. We will now reorder, okay, the buses. And we will use scheme 0. Okay. So we have 10 nodes, nodes 1 to node 10, and then on the second column, we will list the degree. Okay? So for bus 1, merong tatlo siyang off-diagonal elements. So if it's degree number 3. For bus number 2, degree is also 3 because it has 3 off-diagonals. For element number 3 or row 3, the off-diagonals are 1, 2, 3, 4, 5. Hence, you have 5 there. And then you just list. Okay? And then you choose the node with the lowest degree. It's node 9. Degree niya is equal to 1. Okay? It only has 1 off-diagonal element. So it means that yung bus 9 natin, it will now be the new bus 1. Okay? It will now be the new bus 1. Okay? And then bus 6, it is the next bus with the lowest number of degree, lowest degree. So we will now call it bus 2. Siya yung bagong bus 2. And then we have several buses with degree equal to 3, like nodes 1, 2, 4, 8, and 10. So since tayo naman sila, we just write them as is. 1, 2, 4, 8, and 10. Okay? Buses 3 and 7 are also, bus 3 and 5 are tied at degree equal to 5. So, tayo naman sila. So, we just get the natural ordering, 3 and 5. And then, the bus with the highest degree is bus 7, degree equal to 6. So, siya yung bagong bus 9 natin, or node 9. Okay? So, if we reorder the numbering, so we now reorder the numbering that way, it means that the matrix will now reconfigure. Okay? Most of the elements will now be concentrated at the bottom and at the right side. And trust me, guys, when you compute for alpha and beta, alpha will become 110, beta will become 60, and alpha plus beta will become 170. So from 202 that we had earlier, 202 multiplications and divisions, we are now down to 170. Okay? So mas mabilis na ngayon yung inversion process natin. And that's scheme 0 ordering. Okay? Now, how about scheme 1? For scheme 1, it's a little bit complicated. Okay? We will still go through this. We will list the nodes, we will list the degree, and then after identifying the degree, we will determine the degree, we have done that already, determine the degree of all nodes. We will now choose the node with the lowest degree. Okay, so going back to this example, the node with the lowest degree is node 9. So this will become our new node 1. Okay, now in scheme 0, we are naive. We just rearrange them according to the degree. But here we're going to introduce an additional step wherein once we have placed a node in the ordering scheme, we will eliminate that node from the graph and update the degrees accordingly. And in case of a tie, choose the node with the lowest natural ordering and then we return to step 1. Okay? This is also known as the Markowitz algorithm or the PD1 algorithm. Okay? Now, I think the best way to go about this is to demo. Okay? Let's go to the solution. Okay? So let us perform scheme 1 ordering to the same matrix. So the first step is to list the nodes from node 1 to node 10, list the degree, choose the node with the smallest degree, and that's node 9. Okay? And then we will now eliminate node 9 from the graph. Okay? So this graph here is based on that matrix. Okay? So how did we draw that graph? For example, node 1, there are off-diagonal elements at column 2, column 4, and at column 8. Okay? So node 1 is connected to node 2, node 4, and node 8. So na ba, guys? Okay, are you still with me? Okay. So similarly, for say node 7, node 7, it's degree 6. This is node 7. There are off-diagonal elements at column 2, column 3, column 5, column 6, column 8, and column 9. Okay? So this is node 3. It is connected to node 2. There is a branch from node 7 to node 2, node 3, node 5, node 6, and node 9. Meron pa to node 8. Nasundan ba, guys? Okay. So this graph here also represents that matrix. And then for the scheme 1 algorithm, ordering, once we have chosen a node to put in the ordering scheme, we will eliminate it from the graph. So when we say eliminate, we just remove it. And when we remove it from the graph, we will just erase it and then update the degree. So if we remove node 9, we will take this away. We will also remove that branch. Okay, it means that node 7 from an original degree equal to 6, 1, 2, 3, 4, 5, 6, its degree will now go down to 5. Okay, so let's remove node 9. Our graph will look like that. So wala na si node 9 dito. And node 7, okay, node 7 is now down to degree equal to 5. Okay, and this is our new graph to look at. Okay, and then we will now choose the next node in the ordering scheme based on the degree. So here we have the degrees here, and then we will choose the node with the lowest degree, and then we will put it as next on the list. So looking at this, the node with the lowest degree is node 6. Okay, siya lang yung may 2. The rest are 3 or higher. So node 6 will now be our new node 2. Okay? Now, once we have placed node 6 in the ordering scheme, we have to remove node 6 in the graph. Okay? So the graph looks like that. If we remove node 6, nawala na siya dito. It has disappeared. And then let us update the degrees of the affected branches. So this branch disappeared. Effectively, we are reducing the degree of node 5 from 1, 2, 3, 4, 5. It is now down to 4. So node 5 from degree equal to 5, it's now down to degree equal to 4. Similarly, node 7, originally the degree is 5, it is now down to 4. And take note that when we remove node 6, all the branches, we didn't lose any connectivity, a connectivity between any pair of nodes. Okay? Now, let's go back to the table, and then we will now choose the node with the smallest degree. And take note that if there's a tie, choose the node with the lowest natural ordering. So there are several nodes with degree equal to 3. It's node 1, node 2, node 4, node 8, and node 10. So since siya yung may lowest na natural ordering, parang siya yung nauuna before, siya pa rin yung piliin natin na nauuna right now. So, okay, we will now choose node 1 as the next one in the order. Okay? And the next step is we will remove node 1 from the graph. And when we remove node 1, imagine we will remove this. We also have to remove that branch. We also have to remove that branch. And we will remove that branch. So take note that when we remove this branch here and this branch, we are now losing the connectivity between nodes 4 and node 8. When we remove this branch and that branch, we are now losing the connectivity between nodes 2 and node 8. You may argue, sir, connected pa rin naman sila dito eh. But we have lost the connectivity through node 1. Okay? So we have to reinsert. We have to reestablish that connectivity. Similarly, if we remove this branch here and this branch here, we have lost the connectivity between nodes 4 and 2. And that's the reason why we are introducing these branches, these 3 branches. And take note, guys, that when we are introducing branches, we are introducing fields in the network or in the matrix. Okay? So we will remove these 3 branches here, but we have to put this back, itong tatlong to. So node 4, originally, it is a degree equal to 3. We have to update it to degree equal to 4. Because now the number of branches connected at node 4 is, or are, 1, 2, 3, 4. Okay? Yun na siya. Yun yung ibig sabihin ng bold dito. Originally, for node 4, the degree is 3. It went up by 1 to degree equal to 4. Okay? Similarly, node 2, the original degree is 3. It has become 4. Okay, so it has become 4. And then node 8, the original degree is 3. It has become 4. Okay? And then we will now choose the next node based on the degree. And using the updated degree, node 10 is the one with the smallest degree. So node 10 will be the next in the list. Okay? And then the next step, we will remove node 10. Okay? So again, if we remove node 10, okay, if we remove node 10, we're going to lose the, are we going to lose the connectivity between node 3 and node 5? Well, the answer is no, because they are originally connected to that branch. So again, take note, we are not introducing a new branch because connected na sila eh. But when we remove this branch and that branch, we are losing the connectivity between node 5 and node 2. Ayun, no, walang branch connected there between them. We are losing the connectivity between node 5 and node 2. We are also losing the connectivity between node 3 and node 2. So when we remove node 10, we have to introduce 2 new branches to connect node 5 to node 2 and node 3 to node 2. Okay? And then using the new picture, the new graph, we will now update the degree. So node 2, this is node 2, originally it's of degree equal to 4. We will now update it to be of degree equal to 5. And so on. And then, as you might have guessed, the next node is node 4. Kasi even though they are a tie, okay, 4, 4, 4, and 4, we are choosing node 4 because it's originally at the front. So we'll just give it the same privilege. Okay? So put node 4 as the next one in the order, and then you remove that one, and then you keep on doing that. And then when we finish, the ordering yields this. 9, 6, 1, 10, 4, 2, etc., etc. Okay? And once we have renumbered, what will happen to the alphas and the betas? The number of multiplication and divisions for the LU factorization process is now down to 92. And for the backward-forward substitution, it's now down to 56. Okay? Originally, we had 202. It went down to 170 for scheme 0, and it further went down to 148 at scheme 2. Okay? So, from 202, it's 148. Take note, guys, that you only have to do the reordering once, but you have to perform the inversion over and over again dun sa load flow. Okay? Or in the in the Newton-Raphson load flow. Any question, guys, before I proceed to scheme 3? Sorry, scheme 2 pala. Kung wala, I will move on to scheme 2. Scheme 2, it's more complicated. Okay? Again, ganun pa rin yung basis. We have to list. We have to base our decision based on the degree. Okay? But here, the objective is to minimize the number of fields at each step of factorization. So it means that at each step, each elimination alternative is considered and the number of resulting fields is computed. And the elimination that results in the lowest number of fields will be the node that we will put in the ordering. Okay? So step 1, for each node, calculate the number of fields that would result from its elimination, and then choose the node with the lowest number of fields. We're going to choose the node that will introduce the lowest number of fields, the lowest number of additional branches. If there's a tie, we will use the degree as the basis. If there's another tie, then we will just choose the node with the lowest natural ordering. Okay? We place the node in the ordering scheme, eliminate it, update the fields and degrees accordingly, and then we go back to scheme 1, to step 1. Okay? Let's do it through an example. Okay? Again, the first step is we will simulate what would happen if we eliminate all nodes, one node at a time. Okay? So in the original network, this is the original network, the big network. If we remove node 1, okay, are we going to introduce fields? Well, the answer is yes, as we have shown earlier. If we remove node 1, we're going to introduce 3 pairs of fields because we're going to introduce 3 branches. Edge created. We're going to create edges 2 to 4. This edge, di ba? This edge, 2 to 8, this edge, and then 4, 8. So we will introduce 3 edges if we eliminate node 1. If we eliminate node 2, nasan si node 2? This is node 2. Are we going to introduce edges or branches? The answer is also yes. In fact, ang sabi niya rito, we're going to introduce 3 branches. This branch here, 1 to 7. Another branch from 1 to 10. And another branch from 7 to 10. So we'll introduce 3 fields. How about node 3? If we eliminate node 3, we will introduce 6 fields. If we will remove node 4, we will introduce 2 fields. If we're going to remove node 5, we will introduce 6 fields. But if we remove node 6, we will not introduce any fields. Ganon din if we remove node 9. It will not introduce any fields. So essentially, if we're using the fields, the number of fields as the basis, we have a tie between node 6 and 9. Now, how do we break the tie? In case of a tie, choose the node with the lowest degree. Here, node 9 has a degree equal to 1, but node 6 has a degree equal to 2. Okay? So we will choose node 9 as the new node 1. Okay? Now, choose node 9. It has the smaller degree. Okay? And then, after removing node 9, we have to do this all over again. Medyo matrabaho siya. Okay? So, after removing node 9, compute the number of fields if node 1 is eliminated. So, imagine you eliminate that. And as what we have seen earlier, we will introduce 3 edges. And then remove node 2, remove node 3, and so on and so forth. These are the number of fields created. Okay? If we eliminate this node, and the removal of node 6 introduces no fields rather. Hence, we will choose node 6. Okay? And then after removing node 6 from the graph, mawawala na siya. This is how the graph looks like. Wala na siya. Sorry, I wasn't able to paste. But the point here is that when we remove node 6, okay, so we already remove node 6 and node 9. We already have these nodes, 8 nodes, 1, 2, 3, 4, 5, 7, 8, and 10. So imagine what will happen, how many fields will be introduced if we eliminate node 1. So we will introduce 3 fields, 3 fields again for node 1 and node 2, 6 fields again for node 3, etc., etc. And And the node, when removed, okay, the node, if we remove a particular node, that node that will introduce the least number of fields is node 4. Take note that all of them introduced fields. Walang zero dito. All of them introduce fields. All of them introduce edges. But the removal of node 4 introduced only 2 fields. Hence, node 4 is our next in the order. And so on and so forth. Okay? So for scheme to ordering, we are left with this 9, 6, 4, 8, etc., etc. And then after counting the number of multiplications and divisions, after all that effort, yung 148 natin nabawasan lang ng 10. From 148 in scheme 1, went down to 138. So after going through that effort, only 10 multiplications and 10 divisions lang yung na-eliminate natin, avoid natin. Okay? So sometimes it may not make sense to do the scheme to ordering. Maybe scheme 1 is already enough. Okay? Now, to make you fully appreciate the reordering scheme, remember the IEEE 118 bus system. Okay? So this is the bus, this is the test system in your MP1 and MP2. Okay? Let's say that we are solving for the Newton-Raphson, full Newton-Raphson method for this network. Okay? So it means that we have to write the Y bus, and then take note that the Y bus, a lot of elements there will be 0. Okay? Because hindi naman ganun ka-interconnected yung network natin. For example, at bus 9, you only have 2 of diagonal elements. Bus 10, it will only have 1 of diagonal element. Okay? How about this bus here? Bus 89, it will only have 4 of diagonal elements. So I think you already know that dun sa machine problem 1, that most of the elements in the Y bus will be 0. And because of that, most of the elements in the Jacobian will be 0. Okay? Now, if we use the original numbering, okay, if we use the original numbering and construct the Q matrix, this is how the Jacobian will look like. Ito yung itsura ng Jacobian. Take note, it's symmetric. This is J1, J1 is here, this is J2 here, this is J3, and that's J4. Okay, so this is the Jacobian for the 118 bus system. So imagine that it is sparse, okay? It's large and it is sparse. If we will not apply reordering, okay, and solve for the LU factors, this is how the Q matrix will look like. Imagine, there's a vast area here that are 0, and then since we didn't reorder, puro fields na siya ngayon. Okay? The original blanks here were filled up with values. And take note that when we are introducing fields into the network, it means there are more multiplications and divisions. In fact, for the Q matrix, it will have 14,849 non-zero elements, and that will be the number of multiplications and divisions in the backward-forward substitution. But the LU factorization will require 220.5 million multiplications and divisions just to invert the LU factor, just to invert the Jacobian for the 118 system, bus test system. That's 220 million multiplications and divisions that we have to do. Now, what if we apply scheme 0? Again, scheme 0, we just have to list the degree and then reorder the matrix, reorder the numbering based on the degree. And this is what we'll get after scheme 0 reordering. Okay? Siyempre, you will be worried na, kasi without reordering, we know that this is J1, this is J2, J3, and J4. But once we reordered, we're going to lose. The elements of J1 will be, it will be dispersed all over the entire matrix. the elements of J2 and J3 and J4 as well. They are now scattered all over the place. But the good thing here is that when we compute for the Q matrix, let's say, let us now apply the LU factorization. This is now our Q matrix. So we have a large area here that are mostly zero, and we were able to retain those zero values as compared to that one. Okay, we only get fields here at the bottom right portion. Okay, the resulting Q matrix will have 1,869 non-zero elements, okay, as compared to the 14,849. Okay, how about the sandali, nasaan si ano? How about yung multiplication and division? Parang may nawawala yata. Ganito ba talaga to? Well, as you can see naman, I don't think that I have to stress it pa. That the fact that we have more fields there, we have 220 million multiplications and divisions. I don't have the number here right now, but we can just assume that the number of multiplications and divisions in this Spark matrix will be superb or will be greatly reduced. And by having fewer multiplications and divisions, then it means that the inversion will become much faster. Now, how about scheme 1? For scheme 1, we implement scheme 1. This will be the number of non-zero elements. And then, scheme 2, bakit wala? Okay, I think I'm missing. If we implement scheme 2 for the 118 test system, then this will be the new Q matrix, okay? And the required multiplications and divisions to perform the inversion is now down to 2 million from 220 million. So by reordering, we are now 100 times faster. So imagine if the inversion takes, say, 100 minutes, nag-renumber lang tayo ng buses natin. We are now down to 1 minute na lang. And it is much faster. Okay? So I hope at this point you're able to appreciate the reordering scheme. Okay? Any questions, guys? Any questions? Okay. So again, the lecture will be uploaded at YouTube. Okay. So I'll turn this over to Michelle, and then she will upload it at YouTube. So before we go, I'll just have to show you the schedule for the rest of the seminar. Sparsity Techniques. Actually, we have this lecture now. You could rewatch the video. And then I'll just stop the recording. Yeah, I'll just stop the recording.